Morning, students. Today we are going to do a quick recapitulation of the Kohlraush law. So, what does the Kohlraush law mean? Kohlraush law states that at an infinite dilution, infinite dilution means what? That when there is going to be the excess of solvent is added, the molar conductivity, that is conductivity of all the ions from 1 mole of electrolyte of an electrolyte, can be expressed as the sum of the contribution from its individual ions. Now this, when we talk about the molar conductivity at an infinite dilution, we can represent it as the sign infinity, or you can represent it by the sign. Okay. Now, let's suppose if I say that find out the molar conductivity of HCl, molar conductivity of HCl at the infinite dilution. So, according to the statement, what will be the molar conductivity of the HCl at the infinite dilution? It will be what? At infinite dilution, it is equal to the sum of the ions, individual ions present in it. This, as it is having the H plus and Cl minus ion over here. Similarly, say suppose if we ask that molar conductivity, find, write down the molar conductivity for the MgCl2 at the infinite dilution. So over here, what will be it? Mg2 plus for the Cl minus ion. As we are having the two chloride ions, so it will be 2Cl minus. Similarly, say suppose we want to find out the molar conductivity for the acetic acid. So in this case, molar conductivity at the infinite dilution for acetic acid, it is going to be the CH3COO, that is your acetate ion, plus for the H plus ion. This is according to the statement which we have done in the Kohlraush law. Now, what are the applications of the Kohlraush law? Now, applications of the Kohlraush law is what? The first application is calculation of molar conductivity and equivalent conductivity at infinite dilution. Okay, for the weak electrolyte over here. Now, if you look, then when we talk about the molar conductivity, equivalent conductivity, it cannot be determined exponentially, or you can say by just plotting a graph. You cannot represent them. Because why we cannot do by this? Because the conductance of such electrolyte is low, and as well dissociation of such electrolyte is not complete at infinite dilutions. Say suppose, let's take an example over here to understand this. At the infinite dilution for the acetic acid, we know it is a weak electrolyte. Okay. Now, if you're going to put a strong electrolyte in this for calculating it, we put a strong electrolyte. It can be KCl, CH3, COOK, HCl. These are what? These are the strong electrolyte. Okay. Now, in this case, what happens? CH3COOK, when HCl is added in it, it is going to give us a acetic acid plus KCl. Okay. Now, if we know the values of this, then we can calculate the molar conductivity for acetic acid. How? Equal to molar conductivity of CH3COOK plus HCl minus KCl. Okay, let's do one example question over here related to this application. For example, we are given with the molar conductivity at the infinite dilution for NaCl, HCl and CH3COONA. They are what? 126.4, 425.9 and 91.0 Siemens centimeter square mole inverse. This will be unit for each case. Okay. And we want to calculate the molar conductivity at infinite dilution for the acetic acid. So first of all, write down the equation. Plus HCl, it is going to give you a acetic acid plus your NaCl. Okay. So what will be the formula? We want to calculate the molar conductivity for acetic acid, which is equal to the molar conductivity for the sodium acetate plus molar conductivity for the HCl minus molar conductivity for the NaCl. By putting the value, you can find out the molar conductivity at infinite dilution for acetic acid. And the unit again will be your Siemens centimeter square mole inverse. Okay. Second application. Second application is the calculation of degree dissociation. Now, what happens in the case of the degree of dissociation when you are going to increase the dilution? It is going to increase the dissociation. Why? Because just a number of ions are going to increase, it is also going to increase. Therefore, your molar conductivity is Okay. So what I was telling you, that जैसे there will be the increase in dilution, there will be the increase in dissociation. Why? As the number of ions are going to increase, your molar conductivity will also going to increase. Now, this is molar conductivity at a certain concentration. This is at the infinite dilution. So degree of dissociation we represent by the alpha. It is at the molar conductivity at a given concentration divided by for the infinite dilution. Third application. Third application is calculation of the dissociation constant of a weak electrolyte. This Ka and Kb. Okay. Now in this case, like we are having CH3, COOH, NH4OH. So let's suppose we find out the Ka, dissociation constant for a weak electrolyte Ka. So it is C alpha square 1 minus alpha. In the upper application, we have came to know that degree of dissociation is what? Molar conductivity at a certain concentration divided by the infinite molar conductivity. So let's put the value of the alpha over here. C divided by, which is equal to the C square divided by the this. So what is going to happen? This is going to cut with this square. So Ka will be this. So on this basis, we can do the numericals. From these three applications, we get the numericals in our exam. Thank you.